you. Thank you for the introduction and thanks for the invitation. It's a great pleasure to be here. And I'm going to talk indeed about Lozenge Tilings on a cylinder, or equivalently cylindric partitions. And my talk is based on a joint work with Andrew Ahn, who is a postdoc at Cornell now, and Roger von Pesky, who is a grad student at MIT. And before we start talking about Lozenge Tilings on cylinder or cylindric partitions, let me first remind you the definition of an ordinary partition. So an ordinary partition is a sequence of non-increasing, non-negative integers with finitely many of them which are non-zero. So here is an example. And there are many ways to depict ordinary partition. The most used and known one is called Young diagram. And what is a Young diagram? You can think about it as a stack of unit squares in the corner such that they stack in a convex way. And then what is the bijection between ordinary partitions and Young diagram? So the number of squares in each row of the Young diagram correspond to the entry of the ordinary partition. And just the fact that those integers do not increase tell us that they're going to be stacked in a convex way. Here is another way to represent partitions. So one can think about it as a particle system. So you can just simply take a Young diagram and rotate it by 45 degrees. And then we can think about the boundary of this Young diagram. Then there are edges of two types. They're either in 1 minus 1 direction or 1, 1 direction. And we associate each edge in 1 minus 1 direction with a particle and 1, 1 direction with a hole. Then it gives us a set of particles which lives on, z plus 1/2. We can shift it and just deal with integers. And know that, if particle can jump on the left or right, it corresponds to adding or removing a square from this Young diagram. This is a small reminder on ordinary partitions. Let us keep going. And before I give you a definition of a cylindric partition, let me remind you one more object, which is a plane partition. So it can be seen as generalization of an ordinary partition. What is a plane partition? So it is a way of filling boxes of the square grid in a quarter plane with, again, non-negative integers, such that the entries do not increase when we move away from the corner in the direction of our square grid, and only finally many of the entries are non-zero. So here is an example of such a plane partition. And each plane partition can be seen as a stack of boxes in the corner of infinite empty room. So here is our, I hope it's clear that this is a 3D picture. So now I think about this picture just as a corner of the infinite room. And then we can stack a finite collection of unit cubes in a convex way, and they correspond to the plane partition. So what is the correspondence? Each stack of cubes, height of each stack of cubes, for example, this one, it has height 2, correspond to the entry of the corresponding plane partition. So this is interpretation in terms of stack of cubes in the corner. However, it's clear from this picture that also I can think about it as a Lozenge tiling of the triangle lattice, of the whole plane triangle lattice by lozenges of these three types, which are shown in different colors. And our Lozenge tilings have some boundary conditions. In each third of the plane, so in each angle like this, we ask that all but finitely many lozenges, okay, in this case, are horizontal. And if we're in one of two other corners, then almost all of them are in one of the corresponding types of lozenges. And the Lozenge tilings with these boundary conditions are in bijection with plane partitions. Okay. Okay. Also, one more comment. We can, if we think about it as a stack of cubes, then a natural move is to add or remove cubes to this stack of cubes, and this corresponds to the following change for the Lozenge tiling configuration. Okay, finally, let me give you a definition of a cylindric partition, which we're interested in today. Let us consider now a square lattice, which is wrapped around a cylinder, a half-infinite cylinder. Here is a cutted version of such a square lattice. And again, we want to fill boxes of this square grid with non-negative integers, such that entries do not increase when we move away from the boundary of this half-infinite cylinder in the directions of our square grid. Here is an example, and yet again, only finitely many of entries are non-zero. About the cylindric partition, we also can think about as a stack of unit cubes, but this time, instead of the corner, we want to stack our cubes in the infinite room. There is a column in the middle, and what we're doing, we're stacking cubes in a convex way around this column. Or we can think about, cutted version of this cylindric room, and then we just have some periodic boundary conditions. We want the stack of cubes here be the same as on the other part of the boundary. And it is clear from the picture that I also can think about it as a Lozenge tilings of infinite cylinder. And all such a Lozenge tilings would satisfy the following boundary conditions. If we go far away down, then all of the lozenges are horizontal. And if we go far away up, then they alternate between these two types of lozenges. However, such Lozenge tilings with these boundary conditions are not in bijection with cylindric partition. They are almost in bijection. We're going to discuss it. But I want to emphasize that if for plane partition it was a bijection, then here it's not really a bijection. We need to modify it a little bit. Okay. And we want to think about random Lozenge tilings over random partitions. So I need to introduce some probability measure on the set of configurations. And let us focus for a minute on a finite case. Assume that we think about Lozenge tilings of a finite hexagon. Then the most natural measure which we can think about is uniform measure. So all tiling configurations are equally weighted. If I think about it as a stack of cubes, then there is another very natural candidate, which is Q to the volume measure. So I can introduce a measure such that the probability of each configuration is proportional to Q to its volume if considered as a stack of cubes. So we just count the number of cubes in the corner of the room. For this concrete case, it is 19, if I count it correctly. And note that if I ask this parameter Q to be between 0 and 1, then this definition of this measure works well, even if I think about the infinite setup, if I don't force myself to live in a finite case. And if I think about Lozenge tilings of the whole plane with the boundary conditions which we described, that for uniform measure, there is some issues. So we're going to deal with Q to the volume measure for tilings or partitions. Here is an example of two simulations of what's the difference between these two measures, at least for the hexagon. So this is a simulation of a uniform Lozenge tiling, and this one for Q to the volume. And you can see that they clearly give some different behavior. So today we're studying this setup. Okay, so we're interested in cylindric partitions and Q to the value measure on cylindric partitions, where again, each partition configuration, so each partition is the probability of each partition proportional to Q to its volume, where volume is just the sum of entries of our cylindric partition. And as I mentioned before, we can think about it as a stack of cubes around the column in the infinite room. However, now I want to think about it with another interpretation. So let us think about top head, cylinder head. And what we're doing, we're stacking cubes in a convex way around this top head. Distributed as Q to the volume with respect to the Q to the volume measure. And together with Q to the volume measure, I want to introduce another measure, another model on cylindric partitions. But before I do this, let me show you a tiny cartoon, which is going to help us to understand the second construction. This is Jack. Jack likes to wear a top hat and spend time outside. And imagine that, okay, it's snowy day, and each snowflake has a shape of unit cube, and they're falling down from the sky with respect to the Q to the volume measure. So now I can think about this snow which stuck around Jack's head. And this is our model. And Jack has a kid. His kid also likes to wear a top hat, but also he likes to jump on a trampoline. So, now together with Q to the volume distributed partition, I also have some vertical shift. If I'm just taking pictures of these two guys, right, I can fix the zero level as a level of Jack's head. And then in addition to cylindric partition, I have a vertical shift. So apparently it makes sense to think about a pair of a dependent cylindric partition and a vertical shift. And we're going to have two models. One of them is just a cylindric partition, and another one is a cylindric partition with a vertical shift. Okay, so this is a cartoon representation of the model. Let me give you a precise definition.
No, if you're on a cylinder, this means just below some point you have only the horizontal lozenges, right?
Right, absolutely. Like if I go far way down, then if we think about the partition, then I don't want to think about it as a Lozenge tiling configuration, because as I mentioned, there is no bijection. We need to think about this vertical shift as well. So for a minute, I forget about Lozenge tiling configuration and only think about stack of cubes. But then, okay, apparently it makes sense to move the level of the empty room. You know, we have an elevator which is moving now. So, and I have independent partition and the vertical shift. Yeah. And probably the next slide is going to answer your question. So look at these two Lozenge tilings of our infinite cylinder. Note that the picture, the tiling on the right is the same as on the left by shifted down by 1 unit, right? And in terms of stack of cubes, these two Lozenge tiling configurations correspond to the same stack of cubes, but in different empty rooms, where the empty room of the first one can be obtained from the empty room of the second one by moving up all configuration by 1 unit. Note that this empty room cannot be obtained from this one by adding or removing a finite number of squares, as well as this configuration cannot be obtained from this one by a finite number of adding or removing unit squares. Okay, they correspond to the same cylindric partition, but one of them is shifted. And this is the reason why we want to think about a pair of cylindric partition together with the vertical shift. And note that if we think about Lozenge Tilings with our boundary conditions, recall that the boundary conditions are, if we go far away down, then all lozenges are horizontal, and if we go far away up, then they alternate between these two types of lozenges. Then each such a lozenge configuration would correspond to a cylindric partition with some vertical shift. I need to choose, I need to fix a zero level. Let's say this was a fixed zero level, then all others can be obtained by shift of configurations which correspond to this interval. Okay, so then the set of all Lozenge Tilings configurations of our infinite cylinder, yet again with our boundary conditions, correspond to a shifted cylindric partition. So let us introduce another measure, a shift mix Q to the volume measure, which is defined on the set of all Lozenge Tilings or shifted cylindric partitions, and the probability of the pair of independent pair of cylindric partition and vertical shift is given by the following. So again, we want to deal with cylindric partitions which are distributed with respect to Q to the volume, and vertical shift we wanted to be discrete Gaussian. Why this is a good choice of the distribution of this vertical shift, we will see later, but so far, this is just a definition of the model. We deal with independent pairs of cylindric partition and vertical shift.
And U is the general parameter you can choose.
Yes, yeah. Okay. So the most important object in tiling model or timer model is the height function. So let me give you one of the definitions. And when we deal with Lozenge Tilings and think about them as a stack of cubes, then there is a very natural definition of the height function where we simply just compute the height of each stack of cubes. So the height function is defined on vertices of a tiling configuration. And okay, if we, for example, go along this vertical line, then here we don't have any cubes, so the height function is equal 0, 0, 0, and here we start climbing up. So this is 1, 2, 3. Here it stays the same. It's still 3, 4, 5. No, still 4, 5, 6, and so on. And here is a graph of such a height function along this vertical line. Equivalently, I can think about the height function as a function which defined by these local relations. So if we do not cross a lozenge, then the height function changed by 1. If we do cross a lozenge, then it stays the same for the horizontal lozenge. Here are for two other types of edges, our local rules. And the height function defined uniquely up to negative constant by these local rules. In particular, we can reconstruct the Lozenge tiling configuration from the height function. And therefore, the key questions in the Lozenge tiling configurations are related to the large scale behavior of the height function itself and of its fluctuations. Note that in our model, again, we have two models. One of them is shifted partitions and just cylindric partitions. So note that the height function for both of our models vanishes if we go far way down, right? Because all lozenges are horizontal. And if we go far way up, then it is linear. If we deal with the shifted model, then there is this extra minus s, which is our shift. If we start with the non-shifted cylindric partition, which we can think about that, okay, we think only about Lozenge tiling configurations, which are, if we think about them as a stack of cubes, correspond to this fixed empty room. So we can just reduce ourselves for thinking about these Lozenge tiling configurations. And in this case, the height function is, if we go far away up, simply coincide with the y coordinate. Okay, and as I said, we're interested in the behavior of height function itself and of its fluctuations. And the height function of the dimer model is known, of the Lozenge Tilings model, is known to have a so-called limit shape phenomena. You can think about it as a law of large numbers. And as soon as you have this, then the next question is how much these fluctuate around the our limit shape. Okay, and before we start discussing these two questions, let me first state the results. First of all, what we did, we computed the limit shape for the height function for both Q to the volume measure and shift mix Q to the volume measure. They're both the same, given by this formula. It's not very important what it is right now. And if you think about how it looked like, that there is a graph of the limit shape. Note that earlier Borodin showed a result on local statistics, and our only real input here is showing concentration. So this is not our main result. Our main result related to fluctuations. So what we did, we showed that in the case of Q to the volume distributed cylindric partitions, the fluctuations of the height function converge to the Gaussian free field in Kenyon-Okounkov complex structure. Don't worry, I will explain what this means. And in the setup of shift mix Q to the volume measure, fluctuations converge to the same Gaussian free field, but with additional discrete Gaussian shift component. And the goal for the rest of the talk is to clarify these two statements. So I'm going to explain what's written here. Okay. And before we do this, let us consider a toy example where the limit shape and fluctuation scaling limit results are known. Let us think about a simple random walk. A simple random walk which starts at 0 and it's forced to end at x. Then about such a simple random walk, I can think as a uniform measure of up-down path from from one corner of this rectangle to another one, right? So what is this? This is just a graph of with respect to the time. And if we think about the scaling limit when x and t goes to infinity with the slope where the slope remains the same, then it is known that those paths concentrate around this limit shape, which is in this case simply a diagonal of this rectangle. And if you never heard about this before, you can convince yourself that this is indeed the case by computing the number of paths which starts, let's say, at 0, this up and down path, and first go to some fixed point. Oops, sorry. And first go to some fixed point here. So we compute paths which go first here and then go up. Then you will see that the number of such a path is exponentially small with respect to the whole amount of paths, which convincing enough to say that indeed those paths concentrate around the diagonal. Okay, now when we know the limit shape, which is just this blue line in this case, we ask what's going on with the fluctuations, and it's also known that fluctuations in this case converge to standard Borodin bridge. And even more, if we compute the covariance at 2 points S and S prime, then covariance converge to the covariance of the Brownian bridge, which is given by the green function for Laplace on a segment 0, 1. Okay, so this was a toy example about the limit shape and fluctuations. And now about the height function, we can somehow think as a two-dimensional version of the simple random walk. So we have some integer valued function, which is now defined at all vertices of our tiling configuration. So let me tell you some known results and predictions about the limit shape and the height function in the tiling model. And I'm going to focus right now with the example of uniform Lozenge tilings of the hexagon. So right now we're thinking about uniform measure, finite case, Lozenge tilings of the hexagon. And okay, so here is how the typical uniform tiling configuration look like at the large scale. You can see some different behaviors inside the so-called Arctic circle. It is chaotic, and close to the corners it is frozen. And it is known, so now the limit shape of the height function, I can think about this as just a surface which is on the top of my stack of cubes, right? I have this 3D interpretation for the height function, and Lozenge tiling itself can be seen as a projection of this surface. And it is known that those surfaces, they concentrate around some minimal surface which minimizing certain surface tension. This result is known for a large for all dimer model with regular lattices and regular weights. However, in general, it's hard to identify this surface. So we always know that this is a minimal surface which minimizing a certain surface tension. But the hard question is to identify this concrete surface in each concrete result. But in the setup of Lozenge tilings with the uniform measure on hexagons, it is known. So here is a rotated surface. This surface just rotated, and more or less this is how the limiting surface, how the limit shape look like. This surface would approximate this limit shape. And as soon as we know this, the next question is how much it fluctuates around the surface, around this limit shape. Okay, and this is yet again a known result by Leo Petrov. It is known that if we look at fluctuations inside the liquid region, so inside the region where we have some chaotic behavior, then the fluctuations converge to the Gaussian tree field, but in some new conformal structure. So what I mean by this, we should take this disk and map it to a unit disk with some precise map. Here it's written. It's not very important right now what it is. What is important about this map is that it's not conformal. So when we map this disk to a unit disk, we change the conformal structure. So we change the conformal coordinates, and what we get the Gaussian tree field in this new complex coordinate, new conformal structure. So this is simply not true that if we stay there, then we get the Gaussian tree field. We need to change the conformal structure.
What is the intuition for that? Is it the corners of the domain that somehow have an effect match in? I mean, what does this map do that kind of makes it better? Are you smoothing more next to the corner than next to the faces? Or?
Good question. Though there is a general conjecture of how to describe this map, though this map takes in account two things. First of all, the limit shape, which you need to identify in each concrete setup, and also the lattice and weights which you started with.
The limit shape is not a circle in this particular.
No, the limit shape of the height function. The limit shape of the height function, it's some surface. It is something.
The whole limit shape, not just the liquid region.
Yeah.
Sorry.
Yeah. So
it could take into account the corners. It sees the corners.
It sees the corners, however, fluctuations lives only inside the domain, because on the corners there is nothing fluctuating. But yes, it definitely sees the structure of this, of the shape of the limit shape for the liquid region. Yeah. And okay, right. So let me say a few words about the Gaussian tree field, since I need this object. So the Gaussian tree field can be seen as a two-dimensional version of the Brownian bridge. And this is one of the reasons why I want to think about the height function as a generalization in some sense of the simple random walk. And the covariance for the Gaussian free field is given by the Green's function on the domain with zero boundary conditions. Okay. So yeah, here is a general conjecture and result for the Daimler model. But before I do this, let me actually introduce the Daimler model because I didn't do it before. So in general, what we want to think about is a Daimler model where a Daimler configuration is a subset of edges of planar and for us bipartite graph, which cover every vertex exactly once. So here it's shown in blue, and two prototypical examples for the Daimler model are Daimler model on the square lattice and on the hexagonal lattice. And you can see that Daimler model on the hexagonal lattice clearly can be seen as a Lozenge Tilings configurations on the dual lattice. So, and this is a particular case of the Daimler model when we deal with Lozenge Tilings. And so what is known? First of all, as I said, there is a limit shape result. So for the Daimler model on biperiodic planar bipartite graphs with biperiodic weights, it is known that normalized height function concentrate near a surface which maximizes a certain entropy functional. Then as soon as we can identify this entropy functional, then we can take in account the lattice, which we started working with. And then there is a conjecture by Kenyon-Okounkov, which gives you a description of this conformal structure, which I was talking in the example of the hexagon. And so in the case of biperiodic weights with biperiodic on biperiodic graphs, the fluctuations conjectured to converge to the Gaussian free field in some conformal structure, and there is a way to describe this conformal structure in terms of the limit shape and the lattice on which we're working on. So here is a general results and conjectures about the limit shape. And let me know what is known for the limit shape and for the fluctuations. And here, let me know that the Daimler model is very sensitive to the boundary conditions. And by the boundary conditions, I mean the shape, the combinatorial shape of approximations of our domains. And so, as I said, it is known that the limit shape concentrate around a certain entropy maximizer. This is known for all biperiodic graphs with biperiodic weights. And there are some results for some special type of domains, very special shape of combinatorial shape of discrete domains, where people know how to compute both the limit shape and fluctuations. Here in the middle, I want to emphasize one result by Bufetov and Gorin, which is about the hexagon with a hole of a fixed height. So what is important for me right now about it, this is the only non-simply connected domain in the list of all these known results. We will go back to this result later. And two results here, those are joint projects with Dmitry Chelkak and Benoit Lallier, where we introduce a different way to describe this conformal structure. So we introduce some new embeddings which describe this conformal structure. So what we're doing, we want to draw a graph in the very beginning in such a way that on those drawings, the fluctuations converge to the Gaussian free field, such that you do not need to change the conformal structure in there to get the Gaussian free field. And what is nice about this construction, that it should work not only for biperiodic graphs with biperiodic weights, but it works for general graphs with general weights. Anyway, so today we're focused on Q to the volume distributed cylindric partitions and shift mix Q to the volume measure on tilings of a cylinder. Okay. So let me remind you what is our setup. So first of all, we have a Q to the volume measure, which is supported on cylindric partitions. And Borodin introduced a periodic Schur process to study these cylindric partitions. And it can be seen as a generalization of a Schur process, which was introduced by Russkikh and Kenyon-Okounkov to study plane partitions. What is the difference between these two objects is that the ordinary Schur process is known to be determinantal. However, periodic Schur process doesn't have determinantal structure, so it's not determinantal anymore. And to make it determinantal, you need to introduce this non-trivial shift. And let me remind you that we deal with the height function. We're interested in the height function, fluctuations of the height function. It has the following boundary conditions. So in the case of cylindric partitions, it vanishes if we go far away down. And if we go far away up, then it just coincides with y coordinate. And here is our second model. We have shift mix Q to the volume measure, which is supported on the set of all Lozenge tilings of the cylinder, again with our boundary conditions. And in this case, we can think about it as a pair of independent cylindric partition and vertical shift, where the vertical shift distributed as discrete Gaussian. And for this special choice of distribution for this vertical shift, Borodin introduced this shift mix periodic Schur process, which became determinantal. So you need this vertical shift to go back to determinantal structure. And actually, if we think about the dimer model, then it is known to always have a determinantal structure. So this is a good sign that we have chosen a correct distribution for the vertical shift. And yet again, we're interested in the height function, which is also vanishing, but if we go far down, and if we go far up, then it is coincide with y coordinate, but with this shift, vertical shift, which we introduced. And again, here are results. So first of all, we computed the limit shape, both for the Q to the volume and shift mix Q to the volume measure. They're the same. This is a graph of how this limit shape look like.
This is the top hat, but is flipped.
No. So recall this picture. It's not a top hat, which is flipped. Right here. If I think about the Lozenge tiling, and now I draw a graph of the height function, right? Everywhere down, it is 0.
Yeah.
So everywhere far down, it's just 0.
Yeah.
What I can do, I can use a height function as a third coordinate and just draw it around my cylinder, right? I can draw a graph using the height function as a third coordinate, which is orthogonal to the surface of the cylinder. And then since it is just 0 everywhere when I go far down, then it should just coincide with my cylinder, right? And when I go up, it starts growing. So this is what's going on. It started growing quite a bit. Yes, it's a little bit confusing, but so yeah, this is just a graph of the height function. And when I think about this top hat, this is a stack of cubes. So this is not the Lozenge tiling itself. Right. So, and recall that we're interested in fluctuations inside the liquid region. So inside the domain, which is not frozen. And we can see that, okay, like everything what is going down from here is frozen. So I need to identify the liquid region, which starting somewhere here. So I can identify this concrete line because I know the limit shape. And we're interested in fluctuations in this part of the domain. And okay, here are our results. First of all, we showed that in the case of Q to the volume measure, when we deal just with the cylindric partitions, which are not shifted, we get that the fluctuations of the height function converge to the Gaussian free field, and the conformal structure indeed coincide with the one predicted by Kenyon-Okounkov. So here is a picture of the Gaussian free field on a cylinder. So you can see that indeed here and there, the boundary conditions are 0. And you can't really see it, but you can believe me that the boundary conditions on these two sides of the square indeed such that you can glue it to a cylinder. So this is a Gaussian free field on a cylinder. And in the case of the shift mix Q to the volume measure, we showed that the fluctuations converge to the same Gaussian free field. So again, the Gaussian free field in the conformal structure predicted by Kenyon and Okounkov, but with an additional discrete Gaussian shift component. And let me say a few words about methods which we used. Yet again, so for the plane partitions, Okounkov and Russkikh introduced Schur processes to study them. So what is a Schur process? Schur measure is defined in terms of Schur polynomials, where Schur polynomials are some very special type of symmetric polynomials. I'm not going to jump more into details, but this is what it is. And then Borodin introduced generalized these constructions for a cylindric case. So he introduced the periodic Schur process. And yet again, the difference with the ordinary Schur process is that without this extra shift, periodic Schur process is not a determinantal process. However, it is the case for the Schur process. But if you add this vertical shift, then you get a determinantal process. And what we did, we introduced a new formulas for joint exponential moments of the height function for these periodic processes, and those formulas are similar to known formulas given by McDonald processes, which can be seen as a more general case of Schur processes. However, let me say that our formulas do not follow from this result, but they are in agreement with this one. And let me emphasize what is hard in these two models, and actually why do we need both of them. So what we did, we used determinantal structure of the shift mix Q to the volume case to get all these formulas. Then using this determinantal structure and these formulas, we deduce formulas for the unshifted Q to the volume case and show the convergence to the Gaussian free field in this case. As soon as we do this, we go back to the shifted case and get the result that there the fluctuations converge to the Gaussian free field with an additional discrete Gaussian shift component. So yet again, what is good about shift mix Q to the volume measure is that it has a determinantal structure. However, instead of just a GFF, we have GFF with an additional discrete Gaussian shift component, and it's much harder to show the convergence of GFF with this extra additional thing. So what we did, we used determinantal structure to get formulas here, because here, if you just start here, you can't get them because there is no determinantal structure. And prove convergence to the Gaussian free field, which is a simpler object than GFF plus shift plus discrete Gaussian shift. So this is the story. So we really jumped between these two models to get the result. We do not claim that there is no other way to do this, but this is how we got our result. So let me finish with showing a connection with another model, which is topologically very much the same. So let us think about Lozenge Tilings of a hexagon with a hole. Know that this domain topologically equivalent to a cylinder, right? However, if you think about at least Lozenge Tiling configurations on a discrete level, they look very much different from what we have on a cylinder. In this case, there is two ways to define, to choose a random tiling. You either allow the height function on the inner boundary to vary, or you fix it to be the same. So what do I mean here? Let us look at this picture. Now that the height function on the boundary, on the outer boundary, with definition which we gave for the height function, stays the same, right? It's always 0 here. When we go up, it's increasing, and it stays 5 here in this concrete example. And this is the same for these two pictures, which are just two different Lozenge tiling configurations of this domain with the hole. However, now if I think about the height on the inner boundary, then it is different, right? Here it is just 2, and here it's 3. So the height function on the inner boundary does depend on the Lozenge tiling configuration. However, the height function on the outer one does not depend on the tiling configuration. And now if we think about fluctuations, right, if we just think about the difference between the height function and the expectation of the height function, then on the outer boundary, it's just 0. However, here we have something which we need to identify. So, and going back, this is what I said, I can think about it in two different ways. I can either allow the height function to vary on the inner boundary, or I can think that, okay, I'm dealing only with Lozenge tiling configurations, which has a fixed height on the both boundaries.
In any tiling, all the boundary of the hole would be the same height, or this is in any case a constraint that you add?
Yes, it depends on the shape of the hole. If I choose this shape, then it has to be the same. Yes, because
because you count the number of lozenges.
Yeah, remember we had these local conditions for the height function, how the height function change. And the height function on the inner boundary is actually identified by just one value, right? The rest doesn't depend, because the local conditions, you never cross lozenges when you go around the boundary. And then it just depends on the direction of the lozenge. And in this concrete case, they're just all the same. But if I choose a different shape of the hole, then the gradient will stay the same, but the height function itself varies. So it is defined by just one value of the boundary. Okay. Okay. So and these two different models. One of them where we allow the height function to vary, and another one where we don't, are in natural connection with our models with our cylinder. With our Lozenge tilings on the cylinder. So if we think about tilings of a cylinder, the whole set of tilings of the cylinder, they correspond to all tilings of the domain with the hole. And if we focus ourselves on cylindric partitions only, recall that for the boundary conditions of the height function, it corresponds to force this vertical shift as to be 0, which is very much the same as to say that the height function on the inner boundary is also fixed. So just cylindric partitions correspond to the tilings with a fixed height function on a hole. Okay. And here is the result, which I already mentioned before, a known result by Bufetov and Gorin. They showed that if you consider the uniform measure on tilings of the hexagon with the hole, and you ask the height function of the hole to be fixed, then the fluctuations converge to the Gaussian prefield in Kenyon-Okounkov complex structure. This result corresponds to our result, where we showed that for Q to the volume distributed cylindric partitions, the fluctuations also converge to the Gaussian prefield in Kenyon-Okounkov complex structure. Now, what is known about fluctuations when the height on the hole is not fixed? So it is still an open question, though there are some results in a paper in preparation. If you're interested, ask these people. I don't know what is their paper. However, there is a general conjecture. General conjecture in the setup when the height on the hole is not fixed. And it says that for general planar domain, not exactly the hexagon, and for any regular lattice with regular weights for the dimer model, the limited fluctuations of the hole height are given by a discrete Gaussian, and even more, one of the parameters of the discrete Gaussian is predicted to be a Dirichlet energy of the unique harmonic function, which is 0 on the outer boundary and it's 1 on the inner boundary. So here is a conjecture for the fluctuations in the domain with the hole. And what we did, we checked that our setup for a cylinder, so when we have this shift, additional shift, is in agreement with that conjecture. So in our case for our shift mix Q to the volume measure, this distribution of the shift is indeed discrete Gaussian, sorry, and what is important is that this parameter is indeed given by Dirichlet energy, as it was shown on this conjecture. That's it, what I wanted to tell you. Thank you for attention.
You mentioned the random matrix connection. You say that this Guinea is involved. So I wonder what's the random matrix connection.
Okay, yeah. So let me. Here I should emphasize that the methods and tools used in this setup or this this setup to prove the results are completely different than for us for the cylinder, because in this case the Q to the volume measure, for example, is not a Schur process, so they use different methods. What we did is not related in terms of methods to what they did at all. And indeed, there you should deal with random matrices and a little bit different methods to get those results.
Sorry, one more. In the previous slide, one result was a Q and the other not. What is the, I mean, is it for any Q? Is there a specific choice of Q?
Oh, no. Here, this result is for the uniform measure.
Right.
And this one for Q to the volume measure.
So more general.
It depends, because it depends whether if you send Q to 1, you get to uniform measure or not, and the answer is no. So those are just two different measures.
Okay.
But my point is that both of them, actually not this one, but shift mix Q to the volume measure, can be seen as a dimer model measure, where you define it with a weight of edges. So in this sense, it is an agreement. Here, yeah, it's a little bit. This is not true that Q to the volume measure on a cylinder is a dimer measure, so you cannot define weights. But shifted Q to the volume measure on a cylinder is indeed a dimer measure. So it's a little bit different model. However, if we focus ourselves on tilings and forget about dimer model, then conjecture is still the same, and it should work both for dimer measure tilings and Q to the volume tilings.
Mm-hmm.
And in this case, this is how it is in agreement. It is not more general, so those are different setups, and this is what this picture corresponds to in the very beginning. Yeah, those are pretty much different models.
So you're saying that this shifted Q volume thing is correspond to dimer, but this Q to volume does not correspond to dimer.
Yeah, I mean, like it corresponds to restricted dimers, right? In some sense, because I asked that, okay, now I want to deal only with Lozenge tilings, which correspond to these empty room, and then there is a question where I can define edge weights, which will give me the dimer measure on these configurations. And it shouldn't be the case, sorry, it shouldn't be the case, because we know that this model is not a determinantal one. And dimer model is always have a determinantal structure.
And so these two models have the same limit shape?
Yes.
So they have the same limit shape at different federation?
Sorry?
They have the same limit shape at different federation?
Yes, that's
Are
correct.
there any conceptual explanation for this?
The fact that they have different fluctuations, yes, of course, because again, think about the domain as a whole. In one case, you have zero boundary conditions for the fluctuations on both parts, because boundary conditions does not depend on a Lozenge tiling configuration. In another case, you have a zero boundary conditions on one side, but another one fluctuates itself.
Any other questions? No, let's thank Marianna again.